Now we will see distortionless transmission line. We will see next distortionless transmission line. So when will we say the transmission line is distortionless? So in that case, the attenuation constant alpha, attenuation constant is represented by alpha. It should be frequency independent. It should not depend on, or it is not a function of frequency. Alpha should not be dependent on f. It is not directly proportional, or it should not be a function of f. Alpha should not be a function of f. It should be independent of f. While the phase constant is nothing but beta. It should be linearly dependent. Linearly dependent means beta should be simply proportional to omega or f. So in such a case, we will say the line is distortionless. So when will we say a line is distortionless? So when alpha, the attenuation constant of the transmission line, should be frequency independent, while the phase constant beta should be a linear function of frequency. It should be either omega or f. Then such a transmission line, we will call it as distortionless transmission line. So when these two conditions are satisfied, these two conditions should be satisfied, then only we will say the line is distortionless transmission line. Otherwise, it is not the case. So if you see the earlier expression, the lossless line also we have beta is proportional to omega, right? And similarly at microwave frequencies also, but it need not be distortionless. We will see one by one. So for this to be satisfied, alpha to be independent of frequency and the phase constant should be linearly dependent on frequency. This condition has to be satisfied. We will see why this condition need to be satisfied. So only when this condition is satisfied, R by L is equal to G by C, or you can write it as RC is equal to GL. So in order to satisfy these two conditions, so this has to be taken, R by L equal to G by C. So only if we take this condition, then only the alpha, the attenuation constant, will be independent of frequency, whereas the phase constant will be linearly dependent on frequency. So we have to take this condition in order to satisfy the above two conditions. So we will see, we will look at from the expression of the propagation constant. So propagation constant is given by square root of R plus j omega L into G plus j omega C. So from this term you take R common, and from this term you take G common, or you divide. You can take common, multiply and divide, multiply and divide. You can do both. Similarly, you multiply and divide, multiply and divide. So here R will get cancelled. So R and this C I have taken off. So 1 plus j omega L by R and 1 plus j omega C by G. Right? So how I have written this expression? So what I have said, we can take, if we take R by L is equal to G by C, R by L is equal to G by C. Or if you take reverse of it, if you take 1 by, right? If you take 1 by, how you can write? L by R. L by R is equal to C by G. So from this we can write L by R is equal to C by G. Then in either of the term, in place of L by R, so in place of L by R, if you substitute C by C here, then 1 plus j omega g by c into 1 plus j omega c by g. These two terms are same. So square and root will get cancelled. So that's why I have written this is square root of rg as it is, and then as square and root are got cancelled. So this I have written 1 plus j omega c by. So this I have got by using this condition r by l is equal to g by c. From this I have substituted L by R is equal to C by J in this expression. Sorry, here it is C by. You have to substitute C by J. C by G. C by G. Then we will get the propagation constant as square root of Rg into 1 plus j omega C by J. 1 plus j omega C by J. So this is the expression we have propagation constant. So now multiply this term. Now multiply this term with this term as well as this term. Multiply this term with both of these terms. So square root of Rg, this j omega I have written here, and the square root of R by J I have written here, and this is same as C by J. Same as C by J. Now again I will substitute from R by L is equal to C by J, from R by L is equal to G by C. So from this I will take R is equal to GL by C. Simply this L I have taken. So R is equal to GL by C. So this expression for R I will substitute here. The expression for R I will substitute in place of R. If you substitute in place of R, G L by C. So this is same. Here I am not substituting. Only here I am in place of R I am substituting G L by C. So this is square root of Rg plus J omega into square root of, in place of R I am substituting G L by C into G, right? So here we are having G into G, G square. So square and root will get cancelled. So we'll get 1G outside. This is in numerator and this is in denominator. So this is both these will get cancelled, and this C we can write it as root C into root C. So the denominator C and numerator 1 root C will get cancel each other. So if you make those substitutions, we'll get the expression for the propagation constant as it is required for a distortionless transmission line, right? So this is nothing but alpha plus j beta. So for a distortionless transmission line, alpha should be independent of f, right? So here alpha is not a function of f. They are not depending on f. Next slide we will see. So this is the expression we have. So as I have said, z into z, g square and root will get cancelled and g will get cancelled. And similarly this c we can write root lc into root lc. One denominator root lc and numerator root lc will get cancelled. And g will get cancelled. So simply we have root lc. So gamma is equal to square root of Rg plus j omega into root L by C. So if you compare with alpha plus j beta, so alpha is nothing but root Rg, whereas beta is nothing but omega root Lc. omega root LC. So as we have said, alpha is independent of for a distortionless line, alpha should be independent of frequency f, whereas beta should be linearly proportional to omega rf. Yeah. So for a distortionless transmission line, alpha should be independent of f and beta should be a linear function of omega r f. So these two are conditions we are satisfying by taking this condition r by L is equal to G by C. So these substitutions we have, this expression, we have taken the substitution by making this assumption R by L is equal to G by C. So the propagation constant alpha is equal to square root of R into G and beta is equal to omega root LC. So alpha doesn't depend on frequency, it is independent of the frequency as you can see from the expression of the attenuation constant, whereas beta is a linear function of frequency. So here simply beta is simply linearly proportional to f. Omega is nothing but 2 pi f, right? Omega is nothing but 2 pi f. Omega is nothing but 2 pi f. So as these two conditions are satisfied, so we can call this is as distortionless transmission line. So the above conditions we are satisfying by making the assumption R by L is equal to V by C. So this is possible only if you take R by L is equal to V by C. So for a distortionless transmission line, so R by L is equal to G by C. By that means alpha will be independent of it doesn't depend on frequency, whereas beta is a linear function of frequency. Beta is a linear function of frequency. So this is about distortionless transmission line. So for distortionless transmission line, alpha should not be, the attenuation constant should not depend on frequency, whereas the phase constant beta should be linear function of frequency. So then only we'll call that transmission line as distortionless transmission line. For distortionless transmission line, this has to be satisfied. R by L is equal to G by C. Now we will look at the expression for the characteristic impedance. Characteristic impedance. Now we have seen the propagation constant. Now we will see how the characteristic impedance will look like for the distortionless transmission line. So characteristic impedance is nothing but square root of R plus J omega L by G plus J omega C. So here also from the numerator I am taking R as common. From the denominator I am taking G as common. Then we'll get R into 1 plus J omega L by R into 1 plus J omega C by G. So again you can substitute R by L is equal to, for a distortionless line, this has to be taken. So you can take from this, we will get L by R is equal to C by J. So then these two terms are equal. So 1 plus J omega you can substitute in either of the terms. If you substitute L by R is equal to C by J, then these two terms are same. Then you can cancel each other. Then you will get it is square root of R by characteristic impedance Z0 is equal to square root of R by. So for the distortionless transmission line, it is square root of R by. So substitute that and cancel each other. So this is the thing. Then we will get Z0 is equal to square root of so this is the characteristic impedance of for the distortionless transmission line. So this is the expression for the characteristic impedance of a distortionless transmission line. Now again you can substitute. How we got this? We have R by L is equal to G by C, right? R by L is equal to G by C. You can substitute in place of R. In place of R, if you substitute G L by C. So here, in place of R, if you substitute G L by C, then G will get cancelled. You will get square root of L by C. So in place of R, if you substitute G L by C, then numerator G and denominator G will get cancel each other. Then you will have square root of L by C. Both expressions are valid. Both expressions are valid for distortionless transmission line. So this square root of R by G is only for distortionless transmission line. For lossless transmission line, we will have square root of L by C. So whereas distortionless transmission line, we can write square root of R by G or square root of L by C. Square root of L by C. So here also the characteristic impedance, we can write it as R0 plus or minus JX0. So here this is purely real. So there is no imaginary part. Imaginary part is simply 0. So R0 is equal to square root of R by G, that is equal to square root of L by C, and X0 is simply 0. X0 is simply 0. So R0 is equal to square root of R by G, that is equal to square root of L by C. So is it clear or any doubts? Similarly, phase velocity we can find from this. Phase velocity is nothing but omega by beta. So what is beta? Beta is nothing but omega root LC, right? Beta is nothing but omega root LC. So omega will get cancelled. So it is simply 1 by square root of LC. 1 by square root of LC. So phase velocity we can also represent with this small v suffix p. Phase velocity we can write it as, we can represent with u or we can represent with v suffix p. So this is the summary of what we have seen till now. So for a transmission line, so the propagation constant is a complex quantity alpha plus z beta, and the characteristic impedance is also a complex quantity R0 plus or minus j x0. So for a general transmission line, gamma we can write it as square root of R plus j omega L into z plus j omega C, or we can write it as square root of z into y. So this is nothing but the impedance part, and c plus j omega c is nothing but the admittance part. So similarly, the characteristic impedance expression for the general expression is square root of r plus j omega L by g plus j omega C. So that we can write it as square root of z by y. Square root of z by y. So for lossless line, so what we have said, when a line is lossless, for lossless line, we have to substitute R is equal to Z is equal to conductors has to be perfect and the dielectric medium should be lossless. So when will we say the line is lossless? The conductors are should be perfect and dielectric medium separating the two conductors should be lossless. So for that R is equal to Z is equal to 0. So if you substitute R is equal to Z is equal to 0, we will get 0 or simply j omega root L6. So similarly, the characteristic impedance is Z0 is equal to root L by 3. And similarly, distortionless, we will say when alpha is independent of frequency and the phase constant beta should be a function of linear function of f. So for that we have to take r by L is equal to z by c. So this is alpha plus z beta and this is the characteristic impedance for the distortionless line. Distortionless line. So this is the thing that we have seen so far. So we have seen what is propagation constant and what is characteristic impedance, and these expressions at microwave frequencies we have seen, and also we have seen what is a lossless transmission line and what is a distortionless line and the corresponding propagation constant.
If you like the video, please share, like and subscribe. Hit the bell icon to get latest video updates.